Within Chapter 7, we took a closer look at the periodic table. It began with the development of the periodic table and the contributions of Mendeleev and Moseley. With Mendeleev, we considered how he grouped the elements that were known at the time in the mid-1800s based on patterns involving physical and chemical properties. He left vacancies within the table that led to the prediction of new elements and their properties. And we also looked in general terms at when different elements were discovered. With Moseley, his experiment was bombarding different elements with high energy electrons and finding that the elements produced X-rays of a unique frequency. This led to the identification of the atomic number as the number of protons. The first couple pages of Chapter 7, I suggest that you review it. It's general information. I've given a very quick overview right here, but it won't hurt just to revisit that material. Really important idea in Chapter 7 is effective nuclear charge. We find that many properties depend on the electron configuration and how strongly the outer electrons in the atom are attracted to the nucleus. I like this light bulb analogy describing characteristics of effective nuclear charge. It's easy for us to determine the number of protons in the expression, that's what Z is, but there's different ways then that we need to think about the shielding. The way that we found with our simple model was to consider the electrons that have a smaller principal quantum number as being shielding electrons, and with that we could calculate the effective nuclear charge for any electron. We see that for the innermost electrons, the effective nuclear charge just keeps going up, 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 but it's a periodic trend for the valence electrons as they reach a maximum and then reset. So two tasks. Can you calculate the effective nuclear charge for any electron? And perhaps more importantly, can you include the effective nuclear charge in your explanations involving other periodic properties like size, ionization energy, and what we find with electron affinity? Looking at the size for atoms and ions, here's the general pattern that we see. We see that moving top to bottom on the periodic table, there's an increase in size, and moving left to right, the size decreases. Take a second. What are your explanations for those? I would say as we move down the periodic table, there's an increase in n, the principal quantum number. The atomic orbitals are getting larger for the outer electrons, so the atoms are getting larger. As I move left to right, I have an increase in the effective nuclear charge, which is leading to a contraction. What if we're talking about ions? We find that the size for the cations and anions are different than the neutral atoms. Compared to the neutral atom, the cation is always smaller, and the anion is always larger. My explanations for these, if I'm removing electrons, I'm reducing the electron-electron repulsions. So for a cation, it leads to a contraction in the size. For the anions, I'm adding electrons, and these will increase the electron-electron repulsions, so the anion becomes larger. When we're doing these comparisons, many times we're on the lookout for isoelectronic atoms and ions, ones with the same number of electrons. Here would be an example where we see in each case we have 10 electrons, but we see a really clear trend for how the size is changing. Even though they have the same number of electrons, there's different number of protons, so the attraction therefore is different. Take a second, see if you can answer this question. Which of these would be the smallest? Which would be the largest? And how do you explain the differences in size? In order to answer this, I'd first begin by keeping track of what do I have present. How many protons and what is the electron configuration? That would lead me to say that the helium plus cation is the smallest and the hydride anion is the largest. Do you agree? Do you have questions on that? Here's a whole host of questions involving analysis for different neutral atoms and ions in terms of size. You don't have to do all of these, but see if you understand the general idea. I would say most typical on an exam would be something like you see for 7.28, where there's a combination of both neutral atoms and also ions. Let's look more at what does it mean to make things ions. Make atoms ions involves either ionization energy, as we remove electrons, or electron affinity, as we're adding electrons. So we want to first be able to determine the electron configuration for the ions. It's easy for an anion. We're just going to add the electron to the next available orbital. For the cations, we had to be a little bit careful. If you recall, we're going to remove the electron based on the principal quantum number. And with our transition metals, we have to be careful with that. So my suggestion is first determine what the electron configuration is for the neutral atom, and then remove from the larger principal quantum number. Notice with iron, we were moving from the 4s before we began removing from the 3d. When we're discussing ionization energy, we want to be able to recognize the equations that correspond to removing one electron, then the second, then the third. Those are successive ionizations. Removing an electron is always endothermic, and it's really closely linked to the size. A smaller size is related to a higher ionization energy. What is influencing the size? Well, the effective nuclear charge and the principal quantum number. I see a couple exceptions that we've discussed, comparisons involving elements like nitrogen and oxygen. And when we looked at the orbital diagram, we had a good explanation for those too. We saw it was a little easier to remove from oxygen than we would have anticipated because we had paired two electrons in the same atomic orbital, which heightened the electron-electron repulsions. We see in terms of successive ionization, it always takes more and more energy to remove the second, then the third, then the fourth electrons, but we have a large disproportionate increase. We see for carbon, it takes more and more energy to remove the first, second, third, fourth, and then removing the fifth, it was much more difficult, much higher ionization energy, a large disproportionate increase. What would be your explanation for both? Why does the ionization energy increase as I go from the first to the second to the third? And why is there a large disproportionate increase at certain points? Electron affinity refers to adding one or more electrons. We want to be able to recognize the expressions for those. It is favorable when we see a negative electron affinity and unfavorable when there's a positive one. What factors are influencing this? The greater the attraction between an atom and the electron that we're adding results in a more negative electron affinity. So I'm going to look where the electron is going. Is it close to the nucleus? Will it experience a large effective nuclear charge? What would reduce the attraction? Well, if it's going further away from the nucleus, if the effective nuclear charge is small, or if I have to pair it with another electron in the same orbital. These can be competing factors, so it's less clear as far as trends compared to the ionization energy. I certainly see that it's unfavorable to add to noble gases. Why is that the case? Well, I'm adding an electron to a higher energy orbital that's farther away from the nucleus. Consider helium. I'm adding an electron. My notation for both ionization and energy and electron affinity, we're adding it to the atom in the gaseous state. If I then analyze and think about what I've done, well, I know that I have two protons, and I've added this electron now into a 2s atomic orbital. The effective nuclear charge that electron would be experiencing is 0. So it makes sense that it is not favorable to add an electron to an helium atom. Now, if I look at the halogens, it's favorable in every case. Those are my most negative values that I have for electron affinity. What's your explanation for this? Why are these negative values? I think you need to include the concept of effective nuclear charge in your explanation. Chapter 7 ended by consideration of general properties of metals, nonmetals, metalloids, and different groups. The idea was to shift now, and instead of talking about properties for individual atoms, consider the properties of atoms when we have a large collection of them together. We've moved on and we've added more information about this. Periodic properties of atoms themselves are introduced in Chapter 7. In Chapter 8, we go on and think about bonding, and more recently, we've even moved on to consider the structure of solids. What I suggest is read that material at the end of Chapter 7. You've become much more knowledgeable in terms of bonding and the structure of solids. So revisit that material, and I think you might take away different insights than you did when you first looked at it earlier in the semester.